Alright, so in this video we're going to take a look at the control model for the PMSM. And essentially we're taking these equations that we developed in the last few videos, and I say videos because we really developed them in the induction machines, not in the PMSM video. But these equations are going to give us a block diagram model, kind of like we had for both the induction machine and the DC machine. And those kind of models are useful for designing controllers, for doing simulations, for understanding the behavior of these systems. And so essentially we have here two differential equations. I've rearranged them slightly such that ISD and ISQ are on the left side in the first and the second equations respectively. And we're going to consider the general case of the machine, so we're not going to assume that LD and LQ are equal. So in this case we can see what the general model looks like, and if they are equal then we can adjust the model as necessary, but this will be a big picture sort of model. So what's what? We can start by saying that our model will be given, again based on these equations, our model, maybe we can add just a little bit so we can still see the equations a bit. So the model will take signal for VSD, and again this is based on this entire the equations, really. There's nothing else here, right? So we're going to have something coming in here. We're going to have a first order function here. In this case it'll be 1 over SLD plus RS, right? And that's what this side of the equation becomes. And you have the output of that is equal to ISD, again based on the equation. That's what the equation's telling me. But maybe we should make this a bit longer so it's a bit clearer as to what we're doing. And then the output of that will go somewhere, and I'll leave it there for now because otherwise we're going to get way too far ahead of ourselves. And the same thing is going to happen down here somewhere. So let's say, I don't know, over here, down here we have something else comes in, and that something else is obviously going to be VSQ, because what else would it be? VSQ is going to go in here, like so. And VSQ, I guess the output of that will have a second. Well, maybe we can move it further back because VSQ has a extra step, I think. We can have something like this, like that, and this here will be 1 over SLQ plus RS. Right? Again, coming from this equation here, like this. So then the output of this equation, or this box, I should say, not equation, it's not an equation, it's a box, is ISQ, right? That's what the differential equation tells us. And what's on this side, we can, again, leave that for now because otherwise we're going to get a little ahead of ourselves. So let's not do that. So here we'll have two multiplier blocks. And I guess I would have liked to line them up, but that's okay. So there's a multiplier here, and there's a multiplier here. The result of the multiplier goes there. The result of this multiplier goes there. And you also have here omega m coming in. So this is omega m, because omega m, again, needs to be part of your machine model. And omega m goes into this block. This block is a p over 2 block, and the output of the p over 2 block will go to both of these multipliers, and then the multipliers will be multiplied with the current of the opposite side, right? Because that's this LQ omega R ISQ term, and then LD omega R ISD terms. So we're accounting for those as well. And on one side it'll be subtracted, on the other side it'll be added, and I've missed the multiplication here, so let's add the multiplication here by LQ. So here you have LQ, and then I guess we can put the one here, and this one will be LD, and you can send this one up like this, and that will go there, right? Right. Now, the last thing we have to incorporate is, and I probably should move this back because this is the challenging part about drawing block diagrams properly while explaining them, is this should have a P over 2. Well, it should be out after the P over 2. I apologize for that. It should be P over 2 here, straight like this. And this is P over 2. And this goes down. First gets multiplied by lambda m. Lambda m goes down and goes down here. This is being subtracted. This is being subtracted. The output of this, ISQ, is multiplied. Well, first, yeah, see, so we misplaced these things because block diagrams can be challenging to draw. So we have this here. Gets multiplied in with that. So ISD times ISQ. So this is ISD, this is ISQ. The output of here is ISD, ISQ. Maybe we can label that as ISD, ISQ. And then the ISD, ISQ, and what we're trying to do now is we have, what we've done is so far, up to this point. So up to this point, is we've written these two equations. We've done the modeling for the two differential equations, right? So we've generated ISD and we've generated ISQ based on this equation and this equation. Now the next step is to take these outputs and then generate the torque, right? So the torque is the next step. Now how do we generate the torque? The torque is equal to 3p over 4 LD minus LQ ISD ISQ plus 3p over 4 lambda m ISQ. So I'm going to take, so let's get this second term. Well, we've already started the first. Let's do the first term. So ISD ISQ, you multiply the two together. You pass those to a block that is LD minus LQ. And then the output of that will be added to something, and then the output of that will be multiplied by something, and then that will be the final output. At the bottom, you have lambda m, because this is lambda m ISQ, right? And so now you're going to take the output of that, and you're going to add that to this other term that you just generated. And then the whole thing at the end is going to be multiplied by 3p over 4, and that is going to generate for you Tm. So we've just taken these three equations and we've developed a block diagram model. So you would use this for the purpose of control, modeling, for the purpose of simulation, analysis like that, to understand its behavior, and all these kind of things. But there are some things that should be mentioned here because there are some extra things going on here at the same time. So that's the block diagram model. Now you have some other things. You have theta m, which is another thing being measured. So theta m is going to be passed into an integrator. So that's our integrator. The output of that is going to be omega m, right? And if you take theta m and you multiply it by p over 2, then the output of that is theta r. Now, in PMSMs, the rotor flux angle is the same as theta r, and therefore you can measure it by a shaft encoder, which is a machine used to measure the angle. So I guess you can say from shaft encoder, right? So it's a device you can get. And so you can measure theta r by a shaft encoder, which you couldn't do in the induction machine because there's no direct correlation between the rotor flux vector position and theta r. So you need what they call a flux observer. Again, more details than are necessary, but it's just something to be mindful of. Then you also need to somehow generate VSD and VSQ, right? So how do you generate VSD and VSQ? You have a three-phase signal that goes in. And remember, we had these ABC to DQ frame conversions. So we had ABC to DQ, right? So DQ is going to be VSD and VSQ. And this is VSA, VSB, and VSC. But remember, this DQ frame needs to rotate at some speed or some angle, or has to have an initial angle plus a speed, whatever you want to call it, but it needs to be rotational. And the phase or the position of this frame in space at any given time is dependent directly on theta r. So I guess you could draw that over if you want to, but in any case, I mean, this is the kind of system that you have. Maybe we can move all this over because it's kind of cramped if I add another block, which I'm going to. So then, once you have these two, you also need to understand what your currents look like. And if you want to do that, then I guess an extra block that you can include is the dq to ABC frame. And this dq to ABC frame, or transformation, it's not frame, would have ISD and ISQ, and the outputs would be ISA, ISB, and ISC. Now, why do you need these? We'll see later on. I mean, and by later on, I mean like literally like in like 5 minutes or so. But you need to be able to feed back and also understand what the limits and all this stuff are. I guess this is also missing here, so this theta r also goes there. But just a note on the ISA, ISB, ISC, you need to obviously have those feeding back into your current controllers, which we'll look at next. So the next thing we need to do is just understand how do we design current control loops. So far we have a model. The model is great, but we need to take this model, implement it with control loops, and then be able to compare everything as it is. So the equations again that we're going to use, maybe we can take the equations from up here. Let's take these equations here, because these equations will be useful. So we have these equations. Maybe we can get rid of these colors here. For some reason every now and again my pen just stops working, so it seems this might be one of those times. No, we're okay. So what are we going to do here? We have these two equations. What I'm going to do is I'm going to call this thing here, let's call this U Q, and let's call this thing here U, sorry, that was UD, because that's in the D. I don't know why I called that U. UD, and let's call this UQ, okay? So, the same way we did in the previous case for the induction machine, what we can do is you can have control loops, two control loops, and you can have a reference, you can have the output can go to a compensator, the output of the compensator can go to a plant, the output of the plant is the thing you need, and you can feed that back, like so. So this is 1 over SLD plus RS. This is UQ, or D. Let's start with D, because we're starting with D on that side. This is D. Keep confusing the two. And this compensator here is that we can call KD of S. And if you really want, you can call this ED as the error. So this should be subtracted. This should be ISD star. This is the actual ISD. And we can repeat this process for ISQ. So you can have the output like this. And then this goes to the plant. And then the output of this is fed back like so. Subtract there. So you have ISQ star, ISQ actual, EQ, UQ, 1 over SLQ plus RS, and then KQ of S. These are your control loops. Now I should mention that these control loops are designed this way for the purpose of control analysis. When you're implementing these, you have to understand that the output ISQ here is not coming from something like this. If you want to implement this, let's say in a simulation, the proper way to implement this in a simulation is to implement this model here and then measure all the currents and such from this model. The purpose of this model is to, one, give you a working representation of some mathematical differential equations. You can use it for the purpose of control. You can use it even in like sometimes they have like these real-time simulation type of things, and you can program this behavior into a real-time system, and it can actually operate using whatever internal circuitry they have. But the point is, these loops are here for the purpose of analysis. These are not practical implementation things. So if you want to implement this in something like Simulink, this is not what you should be implementing. What you should be implementing is, you should be implementing this model. You should be using this setup, kind of, to generate UD and UQ, which will give you VSD and VSQ, which you would then feed to here, and then go from there. So there's a distinction here to be made, and I mean, this is a challenge for a lot of people, because the idea of control and practical implementations are often, the lines between the two are often blurred. So now, in a case like this, you can have KD and KQ. So KD and KQ can both be PI compensators. And the reason they can both be PI compensators, despite the fact that we are actually dealing with an AC system, is the simplification we made earlier when we did the DQ frame transformation. So that allows us to treat these as DC references or DC circuits, because everything we say is rotating at a certain speed based on theta R, right? So all of that considered, now how do we actually put this together in a real setup? Because again, these are sort of theoretical control loops, but let's put the whole thing together now into one large control thing. I won't put the model and all that stuff together. I'll leave the model at the top, and you can look at that after in isolation. You can compare the two things on a piece of paper or something like that, because it's a good idea to have a good understanding of how everything works together. So our model here is going to look something like this, and it's very similar to the induction machine model, which is kind of what we expect, I guess. We can have one there, and we can have one here, and we can do this. So we'll have some reference coming in, we'll have some measured value there, and this should also be going around like this. And here we have, so why don't we write ISD star there, and then the output here is going to be VSD star, like that. These two are both multipliers. This we can say is KDS, and the output here can be taken like that. And this is again a feed-forward term. We also discussed this in induction machines. This will eliminate, or this will decouple the effect, the coupling effect that we see here. So you see that ISQ adds to VSD, and then ISD adds to VSQ here. So the two are actually related. So to decouple these, we simply take the expression we have, and we apply the negative sign, or the opposite polarity of it, such that the effect of the coupling, I guess, is eliminated. And this is this is a general control concept. This is not unique to this type of machine or anything like that. So we've done this before in the induction machine. And here we have LD, and here we have LQ, and LD and LQ are both multiplied by something that comes into here, block, and goes in like this. So this is P over 2. And if you guessed that this is omega m, then you guessed right. So we have that. This should be subtracted here. That goes around there. At the bottom here, we can have ISQ star kind of come in like this, I guess. And this would be ISQ star. And that would come from your torque reference, right? So you'd want to apply a certain torque, and you would say, okay, this is the torque I want. This is the ISQ I need as a result, because I'm trying to put this into the context of electric vehicles, of course, and the discussions that we're having with all these concepts. So here you would have KQS, and the output of this would be added there, and then the output of that is VSQ star, and this would go down like that. Again, feed forward terms. But before we can do that, we need to also have a term here, and this term here should be ISQ, and this term here should be ISD, and this should be subtracted here, and this here needs another feed forward term. This is lambda m, and so lambda m will be added with omega, or will be multiplied with omega, I should say, and then the result of that will be added here, like so. And then the last thing we need to do is incorporate this ISQ feed forward there. So this is the overall control sequence with feed forwards and everything. Now, a few things to notice. ISD, remember we said this is typically 0, and this is from TM star. So if you imagine for a second your torque speed characteristics that we've seen in the past, the torque speed characteristic would generate some torque. That torque that you need would be converted into a signal for ISQ based on lambda m and p. You remember we have the Tm equals 3p over 4 lambda m ISQ, and so you can convert ISQ to Tm using those, using that equation. Those equations and all those relationships will give you VSD and VSQ references. VSD and VSQ references will come to this here, which will then be passed through the entire model. Then the output here will be Tm, which you can convert, or you can send it to your vehicle model, which will then be converted into a speed, which can then be fed all the way back into the system to compare, to find out where we are on the torque speed characteristic. So the last thing I guess we can close with is a sort of practical view of the whole system. So what would this thing look like if you wanted to implement this in practice? Like if you actually had this, if you had a real vehicle, let's say you had a battery or a battery pack or something like that, you would have to connect that to, let's say this is a DC boost. So this is a boost converter. You would boost the voltage to some value that you need for your inverter. The output of the boost converter would obviously be connected to some DC link capacitor for the inverter. The inverter would be this thing here, so we can say INV for inverter. And then the output of the inverter has to be a three-phase inverter because these are three-phase machines. So the output's there, and the reason I'm drawing these little lines is this way is because you would have to measure these currents. And the third one you don't have to measure, so there's a little trick you can use to get around that. Because if you know two of the currents, you can find out the third one as long as it's a three-phase. So let's say this is your machine, and then the output you would have here like a shaft encoder, and that would go on to the rest of the drivetrain. But this is the part that we're really concerned with. And here, let's say you have an ABC to DQ. So you have a ABC to DQ frame, and what we're doing is we're taking these two signals. So this is ISA, this is ISB, and this is ISC. And you're taking maybe we drew that a bit too close. So let's go down like that. So what you're going to do is you can use this setup. Only two sensors, two current sensors. You can have three measurements or three currents, as long as they are three-phase. If they're not three-phase, you don't know what the third one is. There's no way to know. But in a case like this, what you can do is you can say that. So we know that ISA plus ISB plus ISC is equal to 0. This is what we said, the space phasor, right? So this means that ISC is equal to minus ISA plus ISB, right? So that's convenient. So what we can do then is we can have this current go down. So this is ISA. We can have this one also like this, and this would give you ISB. And then you can take the two of those currents, so this current here, pass that there, this current here, pass that here, and you subtract the two, and then you get ISC. And the output of this is ISD and ISQ for your control algorithms. And this here is basically how we model the shaft encoder, I guess. And that would give you theta M, which you can then convert to whatever you want, internally here or externally if you'd like before that. But the last thing we do is from our control loops, so from our microprocessor or whatever control platform we decide to use, we will have signals. Let's say we have 3 sets of signals. These are PWM, pulse width modulated signals, and they are coming from your DQ. They come from your DQ to ABC conversion. So you would have one signal there, and say one signal there, and this is VSA, VSB, VSC, all star, because they're all references. They would be compared with something in your PWM. Your PWM, depending on which scheme you use, would generate some modulating signal, and then your switching, you would have some switching, I guess. We can add that too if we'd like. So let's imagine this is a triangular carrier at some fixed frequency. And then coming into this DQ to ABC frame are VSD star and VSQ star, which come from your control loop. So ISD and ISQ would go to your control loop, and then VSD and VSQ star would come back from your control loop. So this is the overall system if you were to actually think about it in terms of the big picture. So what we're doing is we're actually modeling all of this stuff, right? So we're modeling, I guess, if we wanted to draw a box around it, we're basically modeling this kind of thing, right? This is the part we're considering. So we model it with equations. In reality, it would look something like this. So let's take a recap, because we've done quite a bit of stuff here. A lot of it was just drawing, I guess. So we took these equations and we developed these models. And the reason I stepped through every single detail of these is because it can be complicated, especially it's not obvious when you look at some of these equations sometimes how you get to these. But we took these equations and we developed this model. And again, this is a machine model for the purpose of control and analysis, and to understand how the things are related. And if you wanted to simulate this, you could do so here as well with this. We looked at some additional blocks like the shaft encoders, the DQ transformations, and all that. And then based on the equations, we looked at how to develop or what the control loops should look like. And you can use, in the case where LD and LQ are the same, you can actually use the same KD and KQ compensators, since these functions end up being the exact same. So we took that then and we developed a giant, well, relatively larger, I guess, compared to these two. We developed a control scheme using those two ideas, and the purpose of these is to decouple ISD and ISQ, well, I should say VSD, VSQ, decouple the two channels, let's say, the D and the Q channels. And that's what these feed forward terms do, this LQ times omega R and so on. And then we looked at a sort of big picture of what it is that we're actually trying to achieve, how we do that in practice, if we were going to do that, and so on. So if you have any questions, leave them in the comments below. Like and subscribe to support the channel, and we'll see you in the next one.